All right, our next speaker in this session is Dr. Sue Marty with the Dow Chemical Company. So Dr. Marty received her Ph.D. in toxicology from the University of Michigan and then did her postdoctoral training at Michigan State University. So there's another MSU connection. Dr. Marty is a science leader in toxicology and environmental research and consulting at the Dow Chemical Company. In her current role, she develops research strategies to evaluate and apply new approach methods for Dow's Predictive Toxicology program. And the title of her presentation is Using NAMs in a NextGen Safety Assessment for a Cosmetic Ingredient.
So I'd like to thank the folks at CRIS for inviting me here today. As Norm mentioned, the title of my presentation is Using NAMs in a NextGen Safety Assessment for a Cosmetic Ingredient. So this is my conflict of interest statement. Obviously, I work for Dow. Strangely enough, we make chemicals, and we do make the chemical that's the topic of this particular case study. So my agenda today is I'm going to talk a little bit about the EU cosmetics regulation and how that drives NextGen safety assessments. Then I'm going to reintroduce the framework for the application of NAMs that Kelly McGurney mentioned in their first presentation. Then I'll talk about a cosmetic ingredient case study using NAMs for the safety assessment. And I'm going to describe the problem formulation and key elements. And here I want to focus on exposure and toxicokinetics, applying cheminformatics, and then using NAMs to evaluate bioactivity and identify a point of departure. And then I'll talk about how we tie the toxicokinetics and the bioactive point of departure into a margin of safety assessment. So in 2009, the EU Cosmetics Directive was passed, and that mandated the need to move away from using animal testing data and safety assessment of cosmetic ingredients. So no data past 2013 is allowed to be used in these safety assessments. So the EU cosmetic market requires only non-animal data in these safety assessments, and this poses a major scientific challenge for assessing some types of toxicity, like systemic toxicity. So I want to describe for you a NextGen safety assessment for a compound called VAN-IPHA. VAN-IPHA is a low molecular weight antioxidant designed for use in face creams, so it's a wrinkle protector, right? So try to prevent wrinkles. Actually, VAN-IPHA has been in our shop for some time, so we do have some in vivo data that was conducted prior to 2013. So we have an acute oral and dermal toxicity study. The LD50 exceeded the limit doses in both cases of 5,000 and 2,000 milligrams per kilogram per day, per kilogram respectively. And then we also have a 90-day oral repeat dose toxicity study. And here at the high dose of 624 milligrams per kilogram per day, we saw a decrease in body weight in the high-dose females, increases in liver weights in the high-dose males and females, and then slight hepatocellular hypertrophy in the high-dose males, which was deemed to be adaptive. So the no observed adverse effect level was 624 milligrams per kilogram per day. We also established that VAN-IPHA is not a dermal sensitizer based on results in the local lymph node assay and the Buehler assay. So one of the things I want to convey today is, this is a great case study for us to try NextGen safety assessments because we do in fact have some baseline in vivo data that we can use to help with these, to see how this NextGen assessment performs. But it's important to understand that the goal of a NextGen risk assessment is not to identify a point of departure for adverse effects. Instead, it's to identify a point of departure for bioactivity. The premise is that if your internal concentration is below one that causes bioactivity, then there's no bioactivity, so there shouldn't be any toxicity. And then, spoiler alert, I do need to say that we did not complete fully this NextGen assessment because the transcriptomics work was not done. That's the last step in this assessment, and unfortunately the company decided not to market the product before we finished that work, but hopefully there's still some interesting things that you'll find from this example. Oops. So this is the framework for the application of new approach methods. So this is what Kelly introduced at the beginning. And we're going to start out walking through the framework just as Kelly describes. We're going to define the problem formulation. We're going to identify key components, and then we're going to consider toxicokinetics. But then, as you see in box 2.1 down here, hopefully I give a pointer, is the adverse effect known? For us, this is a new cosmetic ingredient in development, so no, it's not. So this means we need to look at non-targeted endpoints. Whoops, sorry about that. So this means we need to look at non-targeted assays in order to be able to evaluate that bioactivity across a broad range of targets. Are the NAMS data available, which is in 2.5? No, they're not, so we're going to need to generate data. This is a new ingredient. And then we're going to try and tie that data to what we know about exposure. So in 4.1, is the exposure known? And so for a cosmetic ingredient, we do in fact know what those exposures will be. And then we're going to take our toxicokinetic, physiologically based kinetic model, and we're going to perform forward dosimetry to estimate what an internal dose will look like. And based upon our bioactive point of departure and our toxicokinetics based on the PBK model, we'll try to calculate a margin of safety. So this is our cosmetic ingredient example using NAMS and toxicokinetics for safety assessment for VAN IPHA. Oops. That's weird, it's not. So this is the framework. So the first thing is the problem formulation. So how to assess the safety of this new cosmetic ingredient used in skin cream without using animals. So the key elements we want to focus on will be exposure. So what is the exposure for how the ingredient VAN IPHA is used in cosmetics? We need to characterize compound bioactivity and concentration response relationships in order to identify the point of departure. And then we need to be able to understand internal dosimetry so we can see how that compares with the lowest point of departure. So this is going to rely heavily on toxicokinetics. So we're going to use in vitro to in vivo extrapolation to determine the margin of safety. So margin of safety is defined as the difference between the bioactivity points of departure in the in vitro assays and the internal dose is estimated by our PBK model. And of course, because this is a cosmetic ingredient, the relevant route of exposure will be dermal. So to do this NextGen assessment, we started with a reference from Baltazar, who published a paper on NextGen risk assessment for cosmetics. And what it starts with is this exposure estimate up here in the corner. So it's really important in these kinds of scenarios to be able to have an exposure-led type of approach. So it starts out by characterizing the use scenarios for the cosmetic ingredient as it's used by consumers. It also requires us to really characterize the kinetic parameters, so the ADME, and then also to develop and then ultimately refine a PBK model on what the internal exposure will look like. And the goal of all this work is to be able to understand what the plasma Cmax is. So this is the maximum concentration of the cosmetic ingredient in blood under normal use conditions. So as part of the NAMS assessment, we're going to start with existing information. So we're going to look at in the literature, we're going to look to do read across, and we're going to include in silico computational modeling in order to be able to try and predict what the toxicity will look like. We're also going to do in vitro bioactivity assessment. So this is going to be the data generation in a series of in vitro assays to try and cover a broad array of biological space. And from those in vitro bioactivity assays, we're going to determine an in vitro point of departure. So the difference between our plasma Cmax and our in vitro point of departure will determine our margin of safety and ultimately whether or not we pass the risk assessment. So this is some information on cosmetic ingredients, and actually the habits, practices, and applied doses for different uses of cosmetics have been extensively studied, and the metrics for those are actually quite well agreed upon. So for VAN IPHA, we want to use it in face cream. We're going to use it at a concentration of 0.1%. And so we can calculate the amount of ingredient in contact with the skin for each occasion of use. So it's 0.77 milligrams. We're assuming use 2 times a day, so in the morning and in the evening. And we're assuming leave on instead of a wash off application. So this is an initial PBK model that we developed with GastroPlus, and this is estimating what we think dermal exposures will look like with the 7-day repeat dermal exposure to our cosmetic ingredient VAN IPHA. So now this is very useful information for us to start with because it tells us a concentration range of which we would expect to see the parent. So we know when we do our NAMS studies that we're going to want to include this concentration, but also orders of magnitude above this concentration. The other thing we learned from this is that it looks like VAN-IPHA will reach steady state very quickly following repeated dermal exposures. So also good information for us to know. But this is modeling for the parent compound itself. What we really need to understand is also, do we need to be concerned about metabolites? So this is some in vitro metabolism work with VAN-IPHA. And here we incubated the VAN-IPHA with human liver microsomes and human and mouse skin S9. And so here you can see, here's the chromatogram of VAN-IPHA in buffer. And here you can see that we're seeing the exact same signal in both the human and mouse skin S9. So this suggests there's no dermal metabolism of VAN-IPHA to speak of. When we look at the human liver microsomes, what we find is, in fact, there's one metabolite formed with VAN-IPHA. This was identified as the glucuronide metabolite, and it's not expected to be bioactive. So consequently, what we've established from this work is that we don't have any reactive metabolites of concern. And this is very valuable in NAM work, because that means that when we use in vitro systems that have limited metabolic capacity, we're okay. We don't need to be worried about those metabolites. We can test the parent. So we also were able to confirm this lack of dermal metabolism in our in vitro dermal penetration studies. So I'll talk about that next. So this is our in vitro dermal penetration study. Here we used radio-labeled VAN-IPHA, and it was applied to live human abdominal skin samples. So these are skin samples that are collected at elective surgery, rushed over to the lab, and used immediately to look at dermal penetration and metabolism. We use split thickness skin samples, so instead of full thickness. So this will give us the worst case scenario for the ability of VAN-IPHA to penetrate the skin. And so here you can see this is kind of the chamber model, right? So here's the skin sample in the middle. We're going to put the VAN-IPHA in this donor compartment, or the compound up here in this chamber. We're going to look for the presence of it in the skin samples, and also we're going to collect the receptor chamber. We're going to look for how much is in the receptor chambers, so the amount that was able to penetrate the skin, and also analyze that receptor fluid for any metabolites. Again, we confirmed that there were no metabolites that were found in the receptor fluid, and we estimated the dermal penetration to be less than or equal to 3.5% of the applied dose. And again, this is all information that we can use to further refine our dermal PBK model. So as we're moving down the framework, so we have a pretty good understanding of the toxicokinetics, so now we need to start looking at what NAM data we can evaluate. So to start with, we're going to look at existing data, so what's available in the literature and what's available in silico, and can we do read across. So because this is a new compound, there wasn't anything available in the literature that was helpful. And when we looked at read across, we weren't satisfied that the analogs we could find would be beneficial. So instead, we went to in silico predictive tox modeling with our chem informatics group. This work was actually done concurrently with the TK work that I just showed you. So they went through and they modeled both the parent compound as well as predictive metabolites. Now, our chem informatics group develops both profilers and QSAR models to predict toxicity based solely on chemical structure. So the models, well, we like to have high balanced accuracy. We always try to make the models conservative, so favoring sensitivity over specificity to limit false negatives. So here's the in silico predictions for our parent compound and the predictive metabolites. Here you can see it was negative in a number of the parameters that we used our chem informatic models for, but we did see 3 potential flags. So we had a potential flag for skin sensitization, and this was due to a predicted reactive metabolite. We've already established in vitro that we don't have any reactive metabolites being formed, and we also have a negative LLNA and a negative Buhler. So this suggests that this is a false flag. We also saw some potential interactions with mitochondria, but this was thought to be only occurring perhaps at high concentrations, as well as acetylcholinesterase inhibitor, and this was deemed to be unlikely by our subject matter expert and in addition to support this, we had the 90-day study, no clinical signs, and no changes in functional observations. So we can use some of this existing information that we've generated, and we can include this as part of what we want to look at for our in vitro bioactivity. And so the in vitro bioactivity, I'm just going to run quickly through this given time. We used a number of in vitro assays. Many of these are OECD test guideline compliant studies. So wherever you see these asterisks, there is in fact a test guideline for an in vitro model. So we did skin irritation using epiderm. We did in vitro genotoxicity. We did eye corrosion with the bovine corneal opacity permeability test, phototoxicity and cytotoxicity using the NutraRed uptake. Dermal sensitization, we have in vivo data, but there are in vitro alternatives that are accepted by OECD that we could have used to evaluate that endpoint as well. What I want to talk briefly about next is the 5047 panel and then the cell stress panel. And again, at the end would be those transcriptomics that we weren't able to do. So this is the safety 47 panel. And what this is designed around are the 47 proteins that are most commonly associated with adverse drug reactions. So we can screen whether or not our chemical VAN-IPHA interacts with any of these compounds. And what we found was in fact, VAN-IPHA does not have a non-target interaction with any of these proteins. And this includes acetylcholinesterase, which you will recall was identified as a potential target in our cheminformatics modeling. This is the cell stress panel. So this is another way to look at the potential activity of VAN-IPHA. And here you can see that it was negative in a number of the parameters included in the cell stress assay. And this includes mitochondria. So there's a series of assays that look at mitochondrial oxidative stress. Again, this was a potential target that was identified in our cheminformatics. We did see a positive result in the cell stress panel. So we saw a small decrease in the extracellular acidification rate, or ECAR, in the seahorse assay. And here you can see the dose response here. This is the threshold for a hit, so we only had a response at the highest concentration. So this results in AC50 of greater than 60 micromolar, which was the high concentration. So now we need to take our NAM data that we've generated, put it into context with our external exposure data on the cosmetics and our refined PBK model to estimate the margin of exposure. So margin of exposure, again, is the in vitro point of departure divided by the plasma Cmax. Obviously, the larger the margin of safety, the better the result. So we used the exposure data for our cosmetic application for VAN-IPHA and our refined dermal PBK model, and we estimated that the internal dose at Cmax was 9.0 nanomolar. So the departure, if you will recall, from our in vitro assays, the of greater than 60 micromolar in the ECAR horse assay. So this results in a margin of exposure of about, or margin of safety of about 6,000, which is a pretty good margin between the bioactive concentration and what we estimate internal doses. Now it's important to note this point of departure could decrease if we had the toxicogenomics data available to us. So, this is just an interim margin of safety. And then the question is, 6,000, is that good? So adequate margin of safety, unfortunately, has not been explicitly defined. There has been some work done by the EPA where they looked at in vitro point of departures from 24-hour exposures for a variety of NAMs, and they found that they're generally as conservative as the in vivo studies. So they recommend a baseline margin of safety of 100x or greater. One thing we could do to improve this assessment too as we go forward is we could spend some time doing a better assessment of uncertainty. So did we cover adequate biological space? Could we better estimate population distributions for the Cmax using our PBK model? So could we vary the inputs to better represent the population? Could we estimate distributions for our in vitro point of departure? So if we have that transcriptomic data and a nice dose response, can we look at, for instance, the AC10? And then could we use Monte Carlo for margin of safety where we resample the Cmax based upon the population distribution and the point of departure to get a more representative sample of what we might see across the population. So in conclusion, cosmetic ingredient safety assessments using NAMs are in use and they will continue to be developed. At the moment, there's not a strict guideline for this. They must satisfy the company requirements, and they must stand up to scrutiny by the Scientific Committee on Consumer Safety in the EU. We find that we can evaluate margin of safety between estimated internal doses and bioactivity points of departure. The assessment should be exposure-led and requires some good understanding of the toxicokinetics. We find characterization of concentration dose response data is important to identify the point of departure, and you need to evaluate a broad biological space, and that the margin of safety should include consideration of uncertainties. And lastly, I wanted to highlight that the NAM framework, and this is the one that Kelly used as well, can be used and applied to multiple safety assessment scenarios, including this cosmetic ingredient NextGen assessment. So with that, I just want to acknowledge these folks in my lab who helped with the data generation for this, and thank you.
We have time for one or two questions.
Since you had some initial idea, I mean, it's an antioxidant, so it's not concerning, but you did have some sort of knowledge on potential bioactivity. If you had that, would that target some assays? I mean, we made the choice that we had no knowledge. We do have some knowledge, right? So would that affect it?
Yeah, actually we have a lot of knowledge because back when we were doing those in vivo studies, we actually looked into quite a bit about antioxidants. And there is a reasonable analog. It's not one that you'll find a lot of data on in the literature, but we do know actually quite a bit about that. And we could have driven the testing a little bit more in that direction. You're right. Mm-hmm. We were trying to go from the assumption that we didn't know much about it to see how the NextGen assessment would perform.
But you don't think it would come out any different?
Well, I would love to see that transcriptomics, so I'm trying to still get, as a research project, some additional funding so that I can go back and finish this up and make sure we have a good understanding of how it works throughout. Yeah.
I know you've been very kind with this crown. So for the dermal absorption, did you do just the active ingredient, or was that inside of a formulated product?
It's actually they formulated into the cream that it would be applied in, so it was really very realistic for the cosmetic use.
Have you seen any differences between the active ingredient and like significant differences with a formulated product, the influence of coformulants with dermal absorption?
No, so the reason that the lab chooses, when they do these dermal penetration studies, to use as realistic a scenario as possible. So in fact, we put it all in the carrier and everything, so there wouldn't be any difference between that and the formulation.
Thank you.